Hello everyone, in this session we will discuss about the number representation, memory location and addresses and the memory operations. So in that first topic is number representation. How to represent the number in your computer. So for that we have three systems. In that first one it is a sine, in this first one it is a sine and magnitude. So first one is sine and magnitude system. Sine and magnitude system. So in this, say for example plus 7, how to represent this in the sine and magnitude system. So yes, we know that 1, 2, 4, 8 system. So for 7 it is 0, 1, 1, 1. So in the sine and magnitude also plus 7 will be represented as 0, 1, 1, 1, right. So but the negative number, say for example minus 7. So how to represent the minus 7? Here the most significant bit. So in this 4 bit, the most significant bit is this. So this number it is used to represent the sign. Okay. So for 0, the most significant bit value is always it is if the most significant bit value is 0, then it represents the positive number. If the most significant bit is 1, then it represents the negative number. Okay, here it is a minus 9. How to represent the minus 9 in sine and magnitude system? This is the most significant bit. So this bit is used to represent the sign, right? Here 1. Because it is a minus symbol, right? 1 and 7 is 1, 1, 1. Okay. Take another one example, plus 6. So how to represent the plus 6? So in this it is 0, 1, 1, 0, right? Here also the plus 6 is 0, 1, 1, 0, right? But again take minus 6. How to represent the minus 6 in sine and magnitude system? Yes, in this 4 bit, this is the most significant bit. So it is a negative number. Now 0 becomes 1, 1, 1, 1, 0. So this is minus 6. Okay. So likewise take another one, an example, minus 5. So for 5 it is 0, 1, 0, 1. So for minus 9 it is 1, 1, 0, 1 and so on. This is the sine and magnitude system representation. So in the second one, second representation is one's complement. So one's complement system. So in this one's complement system, again take the plus 7 as the example, right. So plus 7 again it is 0, 1, 1, 1, right, 0, 1, 1, 1, but the negative minus 7 it is different complement. You need to take the complement of each bit. So for minus 7 it is, take a complement of 0, it is 1, take a complement of 1, it is 0, 0, 0. So 1, 0, 0, 0 is the minus 7. It is a one's complement representation for minus 7. Again take another one example, plus 6. Yes, it is 0, 1, 1, 0. So in the one's complement representation for minus 6, it is takes the complement of each bit. So it is 1, 0, 0, 1. So like that. Okay. So this is a second system, and the last and third system is 2's complement system. Next is the 2's complement system. Third one is 2's complement system. Okay. So in the 2's complement system, again here first take the 1's complement of each bit and add plus 1 to that. Okay. Here again plus 7. How to represent the plus 7? Yes, it is 0, 1, 1, 1. How to represent the minus 7 in the 2's complement? Minus 7, first you need to take the 1's complement of this. So 1's complement of this is 1 0 0 0 and add plus 1 for 2's complement. Now 1 0 0 1 is the answer. So 1 0 0 1, it is a minus 7. So this is a 2's complement representation for minus 7. Okay. So next is plus 6. Take a second example, plus 6. For plus 6 is 0 1 1 0. Next is minus 6. So for minus 6, so for that takes the 1's complement 1 0 0 1 and add plus 1 for this. Now 1 1, it is 0, carry and 1 0 1. So 1 0 1 0, it is a minus 6 in the 2's complement representation. And take another example, plus 5 plus 4 plus 2 and so on. Okay. So this is all about the number representation. So in that we are using 3 systems. One is sine and magnitude, and the second one is 1's complement, and the third one is 2's complement method. So the next is addition of positive numbers. So in this 3 systems, so for representation for positive number it is same, but while representing the negative number it is differ from one system to another system. Okay. So here addition of positive numbers. So in that, so addition of positive number, it is very easy, because see here, say for example in the addition of 0 0. So 0 0, it is a positive number, so the answer is 0. So for 1 0, to add 1 0, the answer will be 1. Okay. So the next is 0 1. So again it is a positive number, the answer is again is 1. But for 1 1, 1 1, here the answer is 0 and the carry is 1. Okay, this is a positive number addition. Okay. Next is add and subtraction of the signed numbers, addition and subtraction of the signed numbers. Okay, for this please note down the formula first, then the calculation is very easy. Okay. So what is that formula? Here take an x and y value, x and y, x and y. Here for addition, so x is positive number plus and y is also a positive number, then you need to add, only add x plus y. So this is very easy, just add the value x plus y, right. So in the, this is first one, first formula. Second one, if the x value is negative, minus x, then add with the plus y. So minus x add with the plus y. So in this case you need to take the 2's complement of the x value. So take the 2's complement of x, then x plus y, right. So next formula is, so if x value is positive number, then y value is negative number, then take the 2's complement of, y and then add x plus y, right. So next is fourth one, if both the number is negative, so minus x plus of minus y, then you need to take the 2's complement of both x and y value, then add x and y value. You need to take both 2's complement for both x and y, both x and y. Okay, take an example. So for the first one, plus 2 and plus 3. So plus 2 and plus 3. How to represent the plus 2? Yes. So it is 0 0 1, 0. 0, 0, 1, 0. Next is plus 3, it is 0, 0, 1, 1. So, if both the number is positive, so we are checking the first formula. So, if both the number is positive, then add x plus y, right. So, 0, 1. So, in the previous, yes, 0, 1 is 1 and 1, 1, yes, it is 0 and carry 1. Now, 1, 0, 0, now it is 1, 0, 0, it is 0. So, here 3 plus 2, it is plus 5. Yes, check the answer now. 1, 2, 4, 8. So, 0, 1, 0, 1. So, it is nothing but 5 plus 5. Okay, got it? Take the next example. Take the second example. Here, so minus 2 and plus 3. Minus 2 and plus 3. Right? What is the answer? Yes, it is plus 1. Right? So, minus 2. For plus 2, it is 0, 0, 1, 0. Takes the 2's complement of x. This is x, right? This is y. Takes the 2's complement of x. Now, 2's complement of x is, for 2 is 0, 0, 1, 0. So, after the 2's complement, it is 1, 1, 0, 1. Add 1, it is 0, 1, 1, 1. 2's complement of 2 is 1, 1, 1, 0. Okay. So, for plus 3, it is 0, 0, 1, 1. Now, add these two. So, here 0, 1 is 1, 1, 1 is 0 and carry 1, and again 1, 1 is 0 and again carry 1, 1, 1, 0, again it is 0 and carry, and here we neglect the carry. Okay. Now, so for this 0, 0, 0, 1 is a positive 1. Yes, right, plus 1. Correct answer, right? So, take another one example. Okay, next example, it is okay, plus 2 and minus 3, plus 2 and minus 3. Okay, for plus 2 it is 0, 0, 1, 0, but for minus 3 you need to take the, if x, y is negative, then you need to take the 2's complement of y. So, for that minus 3 is 0, 0, 1, 1 is 3, takes 2's complement 1, 1, 0, 0 and add 1, 1, 1, 0, 1, right, 1, 1, 0, 1. Now, 1, 1, 0, 1. So, now add these two. So, 1, 1, 1, 1. Okay. So, here what is the answer? It is minus 1. It is minus 1, right. So, for plus 1, it is 0, 0, 0, 1. Right, takes the 2's complement. For this, for minus 1, it is 1, 1, 1, 0, add 1, answer is 1, 1, 1, 1. Check this with this. Yes, correct, right? Yes. Okay, now take another one example. So, for the last one, it is minus 2 and minus 3. Minus 2 and minus 3. Okay. For minus 2, again it is 0, 0, 1, 0, takes 2's complement of this, it is 1, 1, 0, 1 and add 1, 0, 1, 1, 1, right. Okay. Minus 2 is 1, 1, 1, 0 and minus 3 is 1, 1, 0, 1 and add these two. So, now answer is, so 0, 1 is 1, so 1, 0 is again 1, 1, 1 is 0 and 1, 1, 1 is 1 and carry 1 and neglect the carry. So, this is the minus 5. So, take the 2's complement of 5, then you will get 1, 0, 1, 1. Yes, correct. Okay, this is for addition. So, next is for subtraction. Again we have same set of formulas, we will check that now. Okay, so here for subtraction, again take two variables x and y. So here x is positive and y is positive, then you need to subtract these two numbers, then you need to take the 2's complement of y, right. So similar way, if x is negative and y is positive, you need to subtract these two. Here you need to take 2's complement of both the numbers, both x and y. So takes 2's complement for both x and y. Okay. So again, if the x is positive but y is negative, then you need to subtract these two. Here no need to worry, directly you can do x plus y, right. So next is, if both x and y value is negative, you need to subtract these two numbers. So in this case, takes the 2's complement of x and add both x and y value. So first is x is positive, y is positive. In this case, takes the 2's complement of y and add x with the y. So though this is a subtraction, you need to take the 2's complement and add x and y value. Okay. Take the same example. So here it is plus 2 and plus 3. So here you need to subtract these two number. Okay. How? So first is 2, it is same, but here it is y value is plus 3, but you need to subtract it. So in that case, you need to take the 2's complement of 3. So it is a 2's complement of 3, 0, 0, 1, 1. So for that 1, 1, 0, 0, add 1, 1, 1, 0, 1 for minus 3, right. Now add x and y value. So for that it is, for 2 it is 0, 0, 1, 0, 0, 0, 1, 0, and for minus 3 it is 1, 1, 0, 1, and add these two. Okay. So 1, 1, 1, 1. Now the answer for this is minus 1. So takes the 2's complement of 1, you will get this answer. Okay. So then take another one example, plus 2 and next is okay, minus 2 and plus 3. Minus 2 and plus 3. So minus 2 and plus 3. So again plus 3, here it is a subtraction. Now you need to take 2's complement of both x and y and add x and y value. So for minus 2 it is 0, 0, 1, 0, 2's complement 1, 1, 0, 1, it is 1, 1, 1, 0, right. So 1, 1, 1, 0, for minus 3 it is 1, 1, 0, 1, and add these two, 1, 1, 0, 1. So neglect the carry, you will get the answer. Likewise, take x and y value. Here x is positive, y is negative. In this, directly you can add x and y value, because minus into minus is plus. And take another one example for x and y. So here both x and y is negative, but here minus into minus is plus, but takes 2's complement of only x value. Got it? Okay. So the next topic is memory, location and addressing. Okay. So the next topic is memory location and addressing. So in this, yes, we have numbers, so we have characters, we have strings, and we have set of instructions. How to represent, how to store all these things into memory. So that is a main thing in the computer organization. So here, so we have numbers, right? We have numbers, we have characters, and we have some set of instructions, machine instructions, right? You need to store this in the memory. How? So here the main memory will be divided into the main memory will be divided into millions of cells, and each cells in that millions of cells, each cells it contains one bit, right? To represent any numbers or any characters, it is not enough that one bit. So for that we group that bits into n bits, okay? To represent number we need n bits. To represent character again we need n bits. To represent the instructions again we need n plus bits, okay? So here what is that bit? It is a group of bits. So here that group of bits, it is called as, in the memory it is called as word. So say for example this is the memory, right? This will be divided into n number of bits. Here n represent the length of the word. So word, it is nothing but it is a group of n bits, right? The length, that n represent the length of that word. So this is the memory location, and this is the first word. So again this is the memory location, it contains n cells, n bit cells, then it is a second word. Likewise, so again this is n bits, so this is the last word in the memory, okay. So here this words and all, okay. But how to represent number, how to store number in this word? So here the number, it occupies full one word, right? This full one word, it is occupied by this number. But character, always the character will be converted into ASCII value, and that ASCII value will be stored in this word. But in the representation, character, once you declare the character variable, it will allocate only 1 byte. Right, but the number, it will allocate 2 or 4 bytes. It depends on the compiler, okay. So here, yes, number, it occupies full one word, but character, it will be again divided into number of bytes, and it occupies only 1 byte, okay. But instructions, yes, it can occupy one word or more than one word, okay. Say for example, if n value is 32, so 32 bit, so that 32 is a word length. So the first word length is 32 bit, and the second word length again it is a 32 bit, and the last word length again it is a 32 word, okay, 32 bit word length. Now see, it is a, as I said, it is divided into 1 bit cell, millions of cell, okay. So see for example this is bit 0, so in this bit 32 bit word length, in this 32 bit word length, this is bit 0 and bit 1, bit 2 and so on. This is bit 31 and this is 30, right. So again here the most significant bit, this B31, it will represent the positive and negative number. If the B31 number is 0, it contains 0, then it is used to represent the positive number. Like that, if this B31, it contains 1, that means this number is negative number, right. This is a representation of number. Next is the character. How to represent the character? How to store the character in this 32 bit? So this will be divided into, this full word will be divided into 4 parts, right, 4 cells, and each cell, it is a 8 bit. It is used to represent the ASCII value. So ASCII character, ASCII value. Okay, so each cell it will contain single character. Say for example, it contains A. Representation ASCII value of A is 65. It contains 65, for example, and another one is B for 66, and so on. Okay. Okay. This is all about representation of number, character, and the instructions. So next topic is byte addressability. So what do you mean by that byte addressability? Address. So take an example, you want to go to your friend house. How you'll identify this is your friend house? So for that you need the particular address, right? So particular house number and street number and area and district and country, etc., right? Here also to identify, say for example, this word, second word contain the number called 65, 64 and 66, any one number. So how to identify that number? So for that your computer will need the address. So that address, you cannot assign address for each bit. It is unpractical, right? So for that we are not using the bit address, here we are using the byte address. Okay. So byte address, we are using the byte address to represent, to identify the particular location in the memory. Okay. So next is big endian and the little endian assignments. What do you mean by that big endian and little endian assignments? See, so take an example of memory. Say it is a 32-bit word length. So in that 32-bit we are dividing into 4 bytes, right? 4 bytes. Yes. Okay. See, so to identify this particular cell you need byte address. So you need to identify this particular word, you need word address. Okay. So here in the big endian concept, the most significant bit, it contains the smallest address. Okay. This is the most significant byte. So it contains the smallest address. So next is 1, 2, 3. After this, so next is, this is 4, 5, 6 and 7, right? This is a word address, this is a byte address. Now the address of this is 0 and the address of this word is starts with 4. Okay. So in the big endian concept, the most significant byte, it contains the smallest address. So byte address, yes, it is 000, right? So take an example for little endian. This is the memory and it is a 32-bit length, word length. Again this will be divided into 4 bytes. Okay, so here in the little endian concept, the least significant bit will contain the smallest byte address. That means 0, 1, 2, 3, 4, 5, 6, 7. So this is big endian and this is little endian. Say for example, John. How to store this John in the big endian representation assignments? Here, so here it is a character, right? It will occupy 1 byte of memory. So J, so this is O, H and this is N, John, right? But in the little endian assignments, the J will be stored here, J, O, H, N. Clear? So in this big endian, the most significant bit contains the less address, smallest address, and in the little endian, the most significant bit contains the highest or the least significant bit contain the smallest byte address. Okay. So the next topic is word alignment. So in the byte addressable format, so always that address will be ranges, the word length, the word length ranges from 16 to 64, 16 to 64 bit. The word length, it ranges from 16 to 64 bits. Say in the word alignment means what? So take an example of any street. So here in the 30-40 sites, it is equal, right? It is aligned, right? Here also the address in the memory, the length of the word, it is similar, it is aligned, it is not unaligned. So I'll tell you how. Okay. So always the address is multiple of 2, right? So in 16 bit, always the word address is like that, 0. So 16 is nothing but it contains 2 bytes, right? So the first word address starts with 0 and the next address it is 2 and the next address, yes, it is 4 and the next address it is 6 and so on, right? If the word length is 32 bit, in this case, so 32 means it is 4 bytes. The word address, it is aligned, right? So for that it is 0, 4, so 4 plus 4 it is 8, 8 plus 4 it is 12 and so on, right? So the next is, if it is a 64 bit, if the word length is 64 bit, so it is nothing but it is 8 bytes. So 8 bytes. So in this case 8 bytes means the word address it is 0, 8, 16 and so on. The word address for 62 bit in the 62 bit word length, so it is 0, 8, 16 and so on. Okay. So the next is accessing the number, character and the character string. So as we know that for number it is a positive or negative, the most significant bit will tells that it is a positive number, this is a negative number and full word will be allocated for each number. Okay. But in the character, again the word will be divided into bytes, so that 1 byte will be allocated for each character. But in the string, say for example John, right? John, how in the big endian method, this is a 32 bit length and John will be stored like this, right? So how your computer will identify this is the end of the string. So for that, to represent the string, at the end of the string you need to give one control signal, right? So that control signal or that control symbol, it is called as null character. You need to add at the end of this string, your computer need to add the null character. This is a special character to represent the string. Okay. So the next topic is memory operations. So here, so in the first session, yes, we know that we have some set of instructions, right? So in that we are studying about different set of instructions, arithmetic instructions, logic instructions and load and store instructions, right? So in the first session, yes, here also same thing. So for memory operation we need 2 instructions. One is load instruction and another one is a store instruction. And the second one is store instruction. So yes, see, if the processor need to execute the program, need to execute the instruction, so for that it need some any data, right? In that case, so your processor need to take the data from the memory to processor, right? To travel the data from memory to processor, we need instruction. That instruction is called load. So here the data will be moved from memory to processor, right? So for example, load, here first you need to take the location address or location A. Say for example, this is your memory and this is the location A. It contain, for example, 2. You need to add 2 number. So here for arithmetic operation you need to store this 2 into the register. So register again it is present inside the processor, right? So here it is a data, it is travelled from memory to processor, location A to R0. So here value of 2, it will be stored in the register R0. Got it? So the next is store instruction. So after completion of the process, again the result will be again stored back into the memory. So for that we need another one instruction. That instruction name is store, right? Say for example, after this add location B comma R0, right? So here after that you need to store the result, addition of 2 number result, right, in the location C. Here first R0 comma location C. This is okay. Here we need location B, right? So 2, 3 example, right? Location A will contain value 2 and location B will contain value 3. So first in this instruction, load instruction, it will take the data from location A and copy that in the R0, right? R0. Now R0 will contain the value 2, right? So in the next instruction execution, addition, right? Location B, here location B value is 3. So location B with R0. Now R0 it contains 2. So 3 plus 2 is 5 and here the result will be again stored in the location R0. Now location R0 value it is 5, right? Next is store. So here store is an instruction. Here you need to copy this 5 into memory, right? R0 contains 5 and location where to store, in the location B, right? Here this is the location B. 5 will be stored here. So in the load instruction, the memory value what actually it contains, it is remaining same. After execution also this remains same. It is untouched in the load instruction, but in the store instruction it may be replaced with the result. Okay. So in the next session we will discuss about